Hi, today we're going to talk about analyzing categorical data, and in our case, chi-square as well as log-linear analysis as chi-square. So first of all, I'm going to talk about chi-square briefly. So what can it do? A couple different things. Number one, it can assess goodness of fit. And number two, it can kind of address the question, how likely is the observed distribution, how likely is that due to chance? Okay, so moving on. When should you use it? Well, in most cases, when you're interested in frequency as well as you're dealing with categorical data, that's when you would want to use it. And in terms of assumptions, we have two different assumptions. Number one, we have the assumption of independence, and number two, no more than 20% of the expected the expected counts are to be less than 5, and all individual counts should be 1 or greater. Okay, so moving on. I'm going to open the first couple packages and then I will talk about the research question that I'm going to analyze. So let's open Gmodels, read Excel, and Maths. Very few packages needed for this. Then we're going to bring in my data, name it chi-square data, and this is where it's located within my computer. And let's take a look at it. All right, so let's talk about my question. Let's say that there's a training, and we're looking at the differences between two forms of compensation. So the first one, we're talking about money as compensation for the training, maybe an hourly wage or something like that. And then secondarily, we're looking at Applebee's, for example, an Applebee's gift card as compensation for the training. Then the other variable we're interested in is gender, male or female. And as an outcome variable, we have pass. Did the person pass, yes or no? Okay, so moving on. First, we're going to factor each of the variables. Gender is going to be factored into male or female. Specify the data name, variable, labels, male or female. Pass is going to be same exact code, except we're substituting pass here. Labels are yes and no, and then training as well. And we're talking about training compensation or reward systems. Specify the variable name as well as the data name, and money or Applebee. So moving on, we're going to do a cross table to begin. And to do that, we're going to have to separate our data into two separate data frames. So we're going to do that by using the subset function. We're going to call it the boys club. Specify the data name, and then we're going to specify the variable that we would like to split. And we're going to do the same exact thing and call this variable girls rule for this subset. And if we want to view what it did, so as you can see, it split it into all males and all females for the other one. So now we're going to create a cross table. We're going to use the cross table function, specify our new data frame that we're using, in this case the boys club. That is our variable of interest, training and pass. And we have multiple different commands here, which I will talk about in a second. And we're going to do that as well for this one. So we have a couple different things going on. First of all, we're telling it that we want to suppress the total proportions. We're telling it to suppress column proportions. We're also saying suppress chi-square proportions, and if we want to standardize the residuals. And that is all included in here. So moving on, we're going to do chi-square as a form of log-linear function. So to do that, we're going to create a linear model to begin. And this one is going to include only girls. So we're going to call this X table and use the xtab function. And we're going to specify training and pass. That equals girls rule, like I said. This is going to take a little bit different of a form as opposed to regular linear models because it doesn't really operate on the same predictor and outcome space as far as when we use the tilde. So let's run that. And if we wanted to view the counts, we could do that by executing the variable name. So moving on, now we're going to produce a saturated model. And to do that, we're going to call it saturated, and then we're going to use the log linear model function. And here we're going to include all of our different variables, and we're going to specify our new data frame that we created. We're going to say fit equals true, which creates a fit variable. So moving on, we're going to expect the chi-squares to be 0 because this is a saturated model. And like I said before, this isn't really the traditional predictor-outcome relationship as far as the formatting of our code is concerned. So now we're going to move on, and we're going to specify a new variable, but this time we're going to exclude the three-way interaction, and we're going to call that no interaction. So as you can see, we've redacted that a little bit to exclude the interaction that we've specified up there. And we're going to call it, we're calling on xtable as our data, and fit equals true. And in this model, our expected values will be included. So moving on, we're going to create another model now. This is called girl saturated model, or girl sat. And this one's going to include everything as well as the main effects. And we can do that by simplifying it and running this code right here. So now we're going to graphically view what we have created. And as you can see, when we produce it, any significant aspects will be shaded, where we said shade equals true. In our case, we don't have any significance, and main equals plot, that is our title. And something to remember when you're referencing this is that size is relative to the frequency counts. We're going to create another mosaic plot now, and this is plot 2, and this is our no interaction model, and another graphical depiction of this. So moving on, we're now going to view the output of our saturated model. As expected, the chi-square value is 0. This is our no interaction model and our girl sat model. So now that we ran it as a chi-square, we're going to do a little bit different of an analysis here, and this is called a log-linear analysis, as opposed to analyzing it within the chi-square frame of reference, whatever you want to call it. So we're going to now call on our original data set using the xtabs function. We're going to specify our model here, and this contingency table is going to produce an output including all of our variables. So you're able to view your counts here. So moving on, we're going to create another saturated model now using the loglinear function, and we're going to summarize that. Again, the chi-squared value is 0. So moving on, we're going to create a variable called three-way now, and what we're doing here is removing the three-way interaction. Now we're interested in two-way interactions, and we can just use the update function instead of typing everything out, and this refers to keeping everything the same. And we have our three-way interaction here. We can view the output of that three-way, and we will interpret these outputs in a little bit. So now if we wanted to compare the models, we could simply use the ANOVA function and specify the two models that we just created. And we can say, how does the model fit change when we remove certain interactions? So moving on, we're going to remove more interactions now. In this case, we're removing training and pass. We're kind of breaking down the model now. And this line of code we're gonna take away. Sorry, in the previous one I said training and pass. This one is gender and pass, if I did mix that up. And we're going to remove gender and training now. So that removes each of those interactions specified. And now we're going to, once again, compare the models that we produced. And that produces output what we're going to be interested in a few is this section here, P delta. In other words, how has this model changed? So now we're going to produce another mosaic plot using mosaic plot. We're going to specify the contingency table that we created previously. Shade equals true. Again, that's going to tell us that that's going to say shade what is significant, and then main equals 3. Plot 3 is the name of our plot, and it is produced there. So moving on, if we wanted to follow up the log linear analysis to say, let's say if we did have significance somewhere, which we haven't necessarily looked yet, then we could do a follow-up chi-square. So doing that, we're going to change our code a little bit from the cross table we did before. The biggest change here is we're going to say chi-square equals true and Fisher equals true, and you will see why in a second. We want the expected values as well, and we're going to want to look at our standardized residuals. We're going to do that for both. Something I do want to point out before we interpret anything, what we should be interested in as far as assumptions are concerned, if I didn't reference this earlier, we're going to be want to look at the minimum expected frequency, and that is above 5. And for this one as well, 7. That is also above 5. So that assumption is good. So moving on, if we wanted to determine the odds ratio, which is semi-equivalent to effect size within chi-square, I kind of created a little function here. And basically what we're doing is I'm telling it I want to plug in A and B, and I want them divided. And that's going to produce a variable called O. And print and paste, I want to see what O is. I want to produce that output. So we're going to run that. And then I derived these numbers from expected and observed counts according to my data. So it's broken down into male or female, and basically we're creating a ratio of ratios. And the prior work I did was just a couple handwritten divisions. For example, in the first one for boys, we have Applebee's training. Did they pass? Yes or no? And that was divided by Applebee's training. Did they pass? No. And the same for girls. And both variables, as far as Applebee's and money, were included. And we're dividing yes and no. So this was the ratio for the first variable, this was the ratio for the second. And now I'm telling R that I want those divided, and that will produce my odds ratio. So let's move on to interpretation. So as far as my hypotheses is concerned, what I'm interested in is, let's say I feel that females will, in the female cohort of all these trainees, I expect training reward to have a significant effect on passing. So we will reference that in a little bit. So first let's look at our output here and see what we should interpret. So as far as these cross tables are concerned, it just kind of shows us a breakdown of our data. For example, what percentage of boys received money and didn't pass, or received money and did pass. And in this case, it looks like it's an even split for Applebee's, no and yes. Same thing for this. We can look at our frequencies as well as the proportion of what they account for. So now we're looking at the saturated model here. And this is our Loglinear as chi-square. And as you can see, we have a chi-squared value of 0, as well as a Pearson's chi-square p-value of 1. So we have a fully saturated model there. Now moving on. It does look like we have significance here. We have a chi-square value of 4.05, or in the Pearson's test, 3.95. and we have a p-value of 0.04. Now we're looking at our saturated model. And it looks like we're marginally significant here. And this was our two-way interactions through a variable where we did remove the three-way interaction. So we do have a two-way interaction significance here. Oh, let's move on. Where were we? Just going back to previously where we were. There we go. So moving on. Now we're going to look at the comparison between the saturated model and the three-way model. It looks like the difference is marginally significant. In other words, the data is questionably fitting. We can't say it's a poor fit because it isn't significant, but as we change from the three-way to the two-way, there is a non-significant change as far as our delta is concerned. Same thing here, we cannot conclude that there's a significant change. And for this as well, the p delta is non-significant. So moving on. Now we're going to look at the cross tables and the follow-up chi-square that we did perform. So for boys, it looks like we have, in both cases with the Yates continuity correction and the Peterson's chi-square test, we do not have significance. So we can conclude within the cohort of the boys, there is not a significant association between training rewards and our outcome variable. Moving on. Now we're going to look at within the girls, was there a significant association? And it looks like there is 1.04 in Pearson's test. So in this case, we can say that there was a significant association found. In other words, we fail to reject the null hypotheses. Well, a hypothesis in this case. And moving on, we have our odds ratios here. And it looks like the odds ratio for the girls is much larger. Okie dokie. Thanks for watching.